Hello. So, welcome to the week 7 live session of the NPTEL course Design of Reinforced Concrete Structures. I am Sanjay Kumawat, and today we will be seeing some questions on curtailment of rebars or the curtailment of reinforcement bars in beam. And the curtailment it is usually required because of the fact that whatever reinforcement bars we are designing and we are providing into the beams or into the slabs, those bars are normally provided for maximum bending moment, but that maximum bending moment it does not exist throughout the structure or throughout the structural component. So in order to take care of this thing, what do? We will be carrying out the curtailment of bars, and this curtailment of bars it is important for the economic design of the structure in order to save the material which are used for the construction of the structures. So let's begin with this class today. Okay, so what do we have here? Firstly, is the theoretical rebar cutoff point. So, what is this? So, let's first try to understand what is this theoretical rebar cutoff point. Let me, okay. So suppose this is a beam, simply supported beam, and it is being loaded with a UDL. This UDL you can take it as W kilonewton per meter or whatever maybe its magnitude. So the for a simply supported beam having a UDL at its top, the nature of the bending moment diagram you can see it here. This is the bending moment diagram, while this is the loaded beam. Okay, so this bending moment diagram, as you can see it here, the mu max it is only at the center, and rest at the other points of the beam the bending moment it reduces. Okay, so the bending moment goes on decreasing from the center of this beam, and at other points and at the central point it is maximum. So while designing this beam, what we consider the maximum bending moment, and for this maximum bending moment we design the beam, and the reinforcement bar it is being provided uh, throughout the longitudinal axis of this beam. But is it necessary to provide such a large amount of bars which is being designed to resist this mu max? No, it is not necessary, because at other position the moment it is less than mu max. So for example, here we have mur, which is the what is MUR? MUR is the limiting moment of resistance of this beam, and we know that the limiting moment of resistance it is somewhere else proportional to AST, because you have that formula 0.87 Fy AST into D minus 0.42 XU, and in the next slide I will be also showing you the relation in between the limiting moment of resistance and the percentage of steel, how they are linearly proportional. That I will be showing you in the next slide. So wait for it. So for the time being, just remember this, like, if mu max is the maximum bending moment at the center of this beam, and mu1 is a moment which is at certain distance from the midspan of this beam. So let's assume that mu1 is 60% of mu max, that is mu1 is 40% less than mu max. So do we is there any need to give the extra bars, the extra 40% bars at the position mu1? No, it is not necessary. So what I am trying to make a conclusion here is, if at the section AA, if it lies at the mid span, then we will have a total of 5 bars. But at a section BB, where the moment it is only 60% of the maximum bending moment, then the rebars which we are providing for mu1 we can reduce it to 60% of AST, because they are directly proportional. So this is the physical meaning of what the curtailment of bars. So normally theoretical rebar cutoff point is what? Theoretical rebar cutoff point is the point where we are trying to reduce the reinforcement by the amount of moment which is less as compared to the maximum bending moment for which the beam is designed. Okay, so now there are other challenges also, why we cannot directly cut off this bar at this point. There are some restrictions. Those restrictions are based upon some observations, and what are all those observations? Let's see them in the next slide. Okay, so I told you that in the what I told you, the moment it is directly proportional to the limiting moment of resistance of a beam. It is directly proportional to the amount of reinforcement provided inside it. So here here I have shown you a graph in between the limiting moment of resistance by BD square and the percentage of steel which is provided inside it. So please try to understand this graph. Here I have Fe415 in combination with M25 and Fe415 in combination with M20. So Fe415 with M25 and Fe415 with M20. Similarly, I will have the other case of Fe250 with M25 and Fe250 with M20. So we have here four cases, and these are the limiting percentage of reinforcement which has been marked over here. So about the limiting percentage, what is limiting percentage of reinforcement? We have studied this in previous classes also. If we provide the number of or the amount of reinforcement, if it exceeds the limiting percentage of reinforcement, that what then what happens, my section it no more remains under reinforced or balance reinforced, but what will happen, it will go over reinforced. And over reinforced design we never prefer it in practical usage, because over reinforced design does not give us enough amount of warning, or it has a nature of failure which is very brittle. Okay, so now let's see what we have in the next slide. Okay, so here I have mentioned the various restrictions on theoretical bar cutoff point, why we cannot directly cut off the bar at the point where I want the moment, where I want the bars to be equal to the reduced moment. So the first reason being is the unexpected shift in the design moment. So suppose I have a beam like this, and it has a UDL upon this, the way we have seen in the previous slide. So for this UDL, the bending moment would be in the shape which is seen in the black curve. And suppose if I have some accidental moment, unexpected shift of moment, suppose I have some moment over this point. So for moment over this point, there would be some shift in the bending moment which is being showed in the red line curve. So now if I curtail my bar directly from that point, which can resist only mu1, but if suppose there is some shift in bending moment, then the moment which is coming at this section, it is more than mu1. So now my beam won't be able to resist that moment. So for that purpose, I cannot really directly curtail the bars at that point. So theoretical cutoff point cannot be the actual cutoff point. And the second reason for this restriction is the development length. Suppose in the beam, if I am cutting my bar from this section directly from this point, then to resist this mu1, there should be some development length, that is the bar should be embedded up to some certain distance, so that there is some bonding between the concrete and reinforcement, and that bonding would ensure that these bars are able to resist the mu1 moment. Now, the third reason behind the restriction on theoretical bar cutoff point is the occurrence of premature diagonal cracks. So we also know that the tensile reinforcement which is present into the beams, this tensile reinforcement it is actually not only responsible for resisting the moments, but it is also responsible for resisting the shear forces. How? Because whatever the resistance which we get from beam, that resistance it is equal to UC plus US, that is shear resistance due to concrete and shear resistance due to the stirrups, and the shear resistance due to the concrete it depends upon the percentage of tensile reinforcement. So if I abruptly remove some reinforcement from a certain section, then there are chances like there would be some formation of diagonal tensile cracks, as you can see in this sketch. Okay, so these are the three restrictions because of which I cannot directly curtail my bar at the point where my bending moment is lower. So I need to extend it up to certain point in order to avoid some uncertainties such as shift of bending moment, and I also need to take care of the development length. And what else I also need to look at is the diagonal tensile cracks. There should not be any formation of diagonal tensile cracks, that is my beam it should not go weaker for the shear forces for which I am assuming it to be resisting. Okay, so now let's see what we have. Okay, now since there are some limitations on the diagonal tensile cracks, sorry, since there are now some limitations on what, on limitations of theoretical cutoff point, is code has given some specifications based upon which the curtailment of the bars are to be carried out. So curtailment of the bars should not be carried out at the point where we wish to reduce the movement, but it should be extended up to a certain distance, and by how much amount it should be extended, we have all this in is 456 2000. So suppose we have a joint. Please try to understand this. If you understand this, further problems would be very easy. If you have a joint like this, and if I draw the bending moment diagram, then that bending moment diagram would look like this. So there will be some negative and positive points. So if I look at this section which I have drawn over here, so I hope now you will be able to visualize it. So this is the bending moment diagram here. This is the bending moment diagram, and here we I have two types of moments, that is firstly being the negative envelope of moment and the secondly being the positive envelope of moment. So the negative envelope, here you can see for the negative envelope, the theoretically zero bending point is at this point, whereas the point where I wish to curtail the reinforcement, that is the theoretical cutoff point, it is at this point for negative reinforcement. And when I talk about the positive reinforcement, the point of zero bending moment it is at this point, and the point of theoretical cutoff point it is at this place. Okay, so I hope now you are able to distinguish in between these four lines. Two of these lines are for zero bending moment, and two of these lines are the theoretical cutoff point. Fine. Okay, now let's see how to provide the curtailment of bars. So now just see this line. Let's first talk about the negative moment envelope. So negative reinforcements are provided at the top. So this is the place where I wish to end up my reinforcement. Some portion of my reinforcement I wish to end up here. But what IS code says, it says that don't end up the reinforcement at this point, but in order to make sure about the amount of development length, or to make sure that enough bonding is happening in between the reinforcement and the concrete, please extend it up to a distance of LC. Okay, so I will summarize all of this point over here. So firstly, what we are talking about, we are talking about the curtailment specifications for negative moment. So what does it says? Firstly, it says beyond the theoretical cutoff point, extend it by LC. And what is LC? LC is it should be greater than D or 12 phi. So this was the first point. What about the second point? Now the second point is, since my negative bending moment it is zero at this point, that is it is zero at this point. Okay, so what one will think that I should end up my bars up to this point only, but is code says even if it is zero bending moment at this point, about one third of the reinforcement it should be extended by a distance of D or 12 phi or clear span by 16. So even if it is zero bending moment at this point, I will extend my bars by these three values, the greater of these three values. Okay, now let's talk about, so this was about the curtailment of bars for negative bending moment. Now let's see what rules we have for positive bending moment. So for curtailment of bar in positive region, see we have this curtailment theoretical cutoff point over here. So I should not stop my bar over here only, but it should again extend by a length of LC, and that LC it should again be greater than D or 12 phi. And secondly, what we have is, and what we have at the point of zero bending moment, what IS code says, don't stop the bars at the point of zero bending moment, but we have here two cases. Extend a bar which is having area of AST by 4 up to the support extending up to the support, and it should extend inside the support by a distance of LD by 3. This was for continuous member, continuous support. And for simply supported, what we have here is AST by 3 extended up to the support by a distance of again LD by 3. So this was the second point, and we also have a third point for the positive bending moment, that is at least minimum of 2 bars. Make sure that you have minimum of 2 bars which are extended into the support. Okay, so this was all about the curtailment rules for negative and positive bending moment envelopes at a joint. So now let's look at a problem on this. Okay, so what we have here is there is a rectangular reinforced concrete beam located inside a building in a coastal town. It is simply supported on two masonry walls, which are 230 mm thick and 6 meter apart. The beam has to carry a distributed live load of 10 kilonewton per meter and a dead load of 5 kilonewton per meter in addition to its own weight. The design midspan section of the beam, so it is asking, acha, the design midspan section of the beam is of for concrete M25 and Fe415 steel. What we are supposed to find here, first one is find theoretical cutoff point of the middle bar, find the actual cutoff point, and find the extension of reinforcement over the support. So, uh, can you tell me what is the difference between the theoretical cutoff point and the actual cutoff point, if you know it or if you can guess it?
So the actual cutoff point is where the bending moment is getting zero, or a reduced value which at which we want to cut it off,
Yes.
and the actual cutoff point is the development length that we have provided, that is LC greater than
Yes, yes.
equals to
Very
that
correct, very
value.
correct. Okay, okay. That's right. So you are getting me what I am trying to solve here, and it is also asking me the extension of reinforcement over the support. So that point, I think that also you are getting what it is asking us to find. So now what we have here is we don't, although we they have given us the live load and the dead load, but they have readily given us the factored design load, and that for that factored design load they have also provided us with the design bending moment, and along with that the limiting moment of resistance which the beam can actually resist is also being provided to us, that is 131 kilonewton per meter. And the section of the beam, it is 250 by 450, and what it is being given here, it is being given that the middle bar is a 25 bar, and the two side bars, they are bars of 20 5. Okay, so these are all the instructions which are being provided to us, and they need, what they need from us is the theoretical cutoff point, the actual cutoff point, and the extension of this reinforcement. So let's see. So what firstly we need to do, we need to find the theoretical cutoff point for the middle bar. So middle bar is 25 bar. So what they are asking us to find is find the point where I can curtail only the middle bar. So if I don't know you whether you will be able to visualize this or not. Suppose this is the section like this, and this middle bar ends here, but the other two bars would be throughout. I need to curtail only this bar, middle bar, and for this middle bar, they are asking us to find the theoretical cutoff point. Okay, so now how would I proceed? How can I find the position of the uh, position of the point where the middle bar would be curtailed? Okay, so I have the limiting moment of resistance, that is 131 kilonewton per meter. This 131 kilonewton per meter is assuming all the three bars. Okay, now what I need to do, I need to find the moment that the beam can take when I remove the middle bar. That is, there shall be only two bars in the beam, and with that two bar at that section, what amount of moment would be resisted by my beam, that I need to find. How will I do that? Can you answer me?
Sir, we will just check the AST value at which the moment reduces, or the moment. Yeah, I think that is the answer.
Okay, so suppose at this point my middle bar it is got curtailed. So in the previous slide I showed you what the moment it is proportional to AST. Okay, so what can I easily say? I can say that for 131 kilonewton per meter, if the amount of reinforcement is 25, means area of 25 this plus area of 2 bars of this, if this can resist 131, then what amount of moment would be resisted by 2 bars of 20 mm. I hope you got this.
Unitary method.
Yeah, what?
Unitary method will follow because it's linearly
Yeah,
following.
yeah, that is proportionality method, linear method. Okay,
Okay.
so here you can see that is the given part. So I have this the total area of bars over here, and this is the reduced bar. That is, after curtailment of 25 bar, what area it remains to me is pi by 4 into 20 square into 2. That comes out to be 628. So if 1119 can resist 131, then 628 will resist what? So it will resist 73.5 kilonewton per meter. Sorry, not per meter, meter. So this is the resistance over this point. Sorry, not resist. Yeah, moment resistance at this point where I will curtail that bar. So now we will have to find the position inside the bar where moment is this. Are you getting me? Suppose I curtailed the bar already. Now for that curtailed section, my beam it can resist only 73.5 kilonewton meter. So at what section of my beam the moment is of this value? That we need to find. So this is the beam, and in the previous slide they have given us the factor design load. So this is 28. Okay, so I have something here and something here. It is a simply supported beam, so I will have this 28 into what? 28 into L by 2. Here also I will have 28 into L by 2. And at what section from the support my moment will be? 73.5. So this is X. Now you can easily find at what distance it will be 73.5. Okay, so you can see it here. WLX by 2, that is this into X minus this UDL, that should be equal to 73.5. That is what it is being written over here. Okay, so this at this X distance I can cut my middle bar. That is, I can provide the theoretical curtailment point. So that X value it comes out to be 1059 mm. Okay, I hope you are getting this. Now also from practical point of view, this question also answers you this fact that in the previous code specification for curtailment we have seen that at least two bars it should extend throughout. So these bars I cannot curtail it. Okay, so the only bar which I can curtail is the middle bar, and that is the reason the question asks us where at which point can I curtail the middle bar, because there is no option to curtail the two sided the bars at the two side. Okay, So the theoretical cutoff point we have already found. Now what I need to find is I need to find the actual cutoff point. I cannot cut the bar at this point because there are some restrictions. Those restrictions we have seen it already. So let's now look at the actual cutoff point. So actual cutoff point, how we will be finding it? Yes, how I can find the actual cutoff point?
Just adding the D or 12 phi,
Yeah,
whichever is greater.
yeah, exactly. So D or 12 phi. So it is coming out to be 399. So what should I do now? 399 is the development length that I should be providing it with along the theoretical curtailment distance. So 1059, it is the distance of the theoretical cutoff point. So what should I do? Plus or minus for finding the actual?
Minus. Minus.
Yeah, it will be minus because this x is from the support. So don't just make out some mistake. We will have to extend the bar beyond this theoretical cutoff point. So now I think you are getting this. So that comes out to be 660 mm. Okay, so that's what all about this problem. Okay, okay. Now again, the third point was also there. We need to also determine the extension of the reinforcement over the support. So do you remember how much we should extend it? We should extend it by LC by 3. What is LC? LC is anchorage length or the development length. Do you remember the? For I have not included that anchorage development length formulation in this slides, but I hope you all remember. So LD development length, it's roughly come out to be 45 from the IS code clause of 26.2.3.3. And you also have the formula, this one you can calculate either from this formula, or you have a table in is code based upon the fy and the fck value. So top, that is the shear, the bonding stress, it depends upon the fck value. So considering all of these points, we have this table for m25 and for fe415. 45 would be the development length. So multiplying 40 into 5, what I will get is, what value will I get? I will get 800 mm, and the extension of my bar into the support will be LD by 3, 267 mm. Now again, I think there is one issue. In the question, if you had read it properly, if this is my simply supported beam, suppose this is the simply supported beam, and my support, they were given to be of weight 230 mm. How can I extend my bar by 267 mm when my support is only of 230 mm? What should I do it now?
We need to increase the width of the bearing.
Width of the bearing I cannot increase. That is the limitation. It is being given in the question. We have a wall of 230 mm and the beam is lying on that. Now you,
So
ah,
we have to bend it up, the bars.
yeah, very good. So what we can do? We can bend the bar. That is, we can, to take care of the extra development length which I cannot provide into this distance. To take care of that distance, I can provide an anchorage of that distance like this. Okay. So this is what I have shown up here. We can actually bend the bar and all the other requirements which was this is the development length by which I had extended beyond the theoretical cutoff point, and by adding up this, I will get the actual cutoff point. That is the actual cutoff point from the support is 660 mm. So this was all about this question. Now this is fine. We have studied the curtailment of bars in the tensile zone. That is what we are, what up to now what we have studied the curtailment of tensile bars. But somewhere in the previous classes and somewhere conceptually we have studied that the design of reinforcement which we are which we for which we are designing these beams, those shear design, it also depends upon this tensile force, tensile bars, because the beam, the shear resistance of the beam, what we are considering it to be, that shear resistance, it is equal to what? It is equal to shear resistance of concrete plus shear resistance of stirrup. But the shear resistance of concrete, it depends upon which two factors? Firstly, it depends upon the grade of concrete, m anything number it can be, m25 or m20. And the other thing, it depends upon the percentage of tensile steel. I am abruptly just removing the percentage of steel at any section, but that would definitely disturb my shear resistance of the beam. So to take care of that, we have some other codal provisions in is 456. So let's look at them. There are some curtailment required for shear strength of the component, structural component also. So one of these three has to be satisfied. So the first one is the shear force at the cutoff point, it should not exceed two-thirds of the shear resisting capacity of the section. So this is the first part. Shear force which is coming from the top, it should be less than two-thirds of the resisting capacity of my beam. Okay, so I need to make sure the first point, if the first point it does not, uh, if like it does not exist, or what should I say, if it does not meet up the conditions, then I should go for the second point. Excess stirrups are provided over a distance of 0.75 d from the cutoff point, having an area of ASV and a spacing of SV. Okay, so suppose if my this condition is not satisfied, then what I will do, I will have to provide some extra stirrups. Okay, so suppose if I am curtailing my bars from this point and my this condition is not satisfied, that is my shear resistance, it is less than two-thirds of the forces which are coming from the top. So what provision we have is, I will have to provide some extra shear reinforcement whose area and spacing are as mentioned in the IS code. So now, and that shear reinforcement, it should extend up to a distance of 0.75 into the curtailment zone. So in this zone means, so now I have a question for you. Should I provide the reinforcement towards the support by a distance of 0.75, or should I provide the reinforcement towards the mid span up to a distance of 0.75, the extra reinforcement, extra shear reinforcement? What do you think? Suppose my this yeah,
Towards the support,
why?
because there the percentage of steel is less
Okay, that's fine.
longitudinal.
Yeah, I agree, there's the percentage of steel is less, but what we have, since I have reduced the amount of reinforcement, if you see the nature of failure which I had showed you in the previous slide, the diagonal tensile, let me go, I should have put it in this slide only. Okay, so if you see the nature of failure, which is because of the absence of, or because of the curtailment of the bars, if you see the nature of failure, it is diagonal tensile failure, and that failure, it propagates towards the middle of the span. This is from the observation from various experimentations. So you can see, because of the less number of bars, or because of the curtailment of tensile, both the crack. So in short, if you don't remember which side I should provide it, simply the simple answer would be, the smart answer would be, just provide it in the direction where the crack will occur, because my ultimate goal is to protect my structure from this crack. So I will provide the extra reinforcement in the direction of this crack. Okay, so the correct answer is, like, you should provide it towards the mid span, because my section is now more vulnerable at the mid span direction. Okay, there I went. Okay, so this was the second clause. Now, what does the third clause says? If neither of the first two I am able to follow, then what should I do for 35 phi? that is for 35 diameter of bars, or the bars which are smaller than this dia, the continuing bar should be provided at least twice the area required for the flexure at the cutoff point. That is, for example, we have curtailed it for MUR1, then the flexural reinforcement which was continued at the bottom, it should be twice the amount of reinforcement which is required for resistance of this reinforcement at that curtailment point. This is not the maximum one, but this is the moment which is at the curtailment point. And at that curtailment point, if AST1 if is the amount of reinforcement required to resist this moment, then if my shear requirement are not being satisfied, then I would be providing twice the amount of reinforcement which is required to resist the moment at the curtailment point. So one of these three condition it should be satisfied in order to ensure that my beam it is safe in shear when I carry out the curtailment. So let's now look at the one problem. So a rectangular reinforced concrete beam. So this is a again the continued problem only. The first problem, in the first problem, what we did, we have provided an actual curtailment of 660 mm from the support. So now because of that curtailment, what will be the effect on my shear reinforcement? So this problem I have provided in continuation, and again this problem I have also taken for the design of beams. So the complete solution of this problem we have already done this. You, if you want to see the summary, you can combine all of these three problems and can have an actual type of design, like an actual visualization of a design. Okay, so the rectangular reinforced concrete beam located inside a building in a coastal is simply supported on two masonry walls. Again the same question. The beam has this. The design midspan section of the beam using M25 concrete and Fe415 steel, it is shown below. Where is it? Okay. The beam is also provided with two-legged 8 mm dia stirrups. Okay. The middle 25 mm dia tensile steel is to be curtailed at a distance of 660 mm. We have solved this 660 mm. So check the reinforcement requirement, shear reinforcement requirement according to IS 456 2000 codal requirement. Okay. So now what we will do, suppose this was my beam. I have curtailed the middle bar up to this point and I have the extension of the other two bars. So at this point, what will I have to find? I will have to find what is my resistance. Shear resistance would is equal to UC plus VUS. VUS is not changing because I have not done anything to VUS, but VUC is changing. Why? Because I have curtailed the middle bar. So at a distance of 660, what I need to again find, what I again need to revise, I need to revise VUC. So what will I do at this point?
Yeah, check the percentage of steel.
Yeah, I will have to check the percentage of steel. Based upon that percentage of steel, I will again have to find VUC. Then I will have to check whether that VUC added up with this VUS, whether that is two-third of my shear force which is coming from the top. And the shear force which is coming on the top, it can be calculated from UDL, which was 28, because this is the previous problem only. So my shear resistance, it should be at least two-third of this shear force. So let's look at this problem. So the percentage of steel at the curtailment point, 628. How did we got it? Pi by 4 into 20 square into 2, because now we have only two bars at the curtailment point, and I divided it by the cross section. This is the percentage of steel. Now I have what? I have M25 concrete. So for M25 concrete and 0.63 percentage of steel from IS code, you can what you can find the design shear stress. So which is coming out to be 0.45 MPa. Okay. Now I also need to by using this design shear stress, you can calculate the design shear force, and also you need to see the maximum shear stress because of the concrete. Okay, so I have done that in the next slide, but before that, what we are finding the shear force which is being resisted up by the stirrups. This is the formula: 0.87 Fy ASV d by s, spacing it is being given 200, and d also we have 319. Everything if you substitute, you can get VUS. Adding this to what you will get the shear resistance at the curtailment point. So before that, I previously told you we need to also take care of the maximum shear force, which is being to avoid any diagonal crushing failure. So the lesser of these two value would be my actual shear resistance at the curtailment point. So 97.3 is the amount of shear which can be resisted at that point. Now what we have to determine now, we have to find what is the shear which is coming at that point. So if this is 28.1, if this distance is 660, so what will be this value? 28 L by 2. So now what is the shear force at this point? What will be the shear force at this point? 28.1 L by 2 minus this value. This is 28.1 into 0.66. That is, I'm taking it in meter. So this is the shear force which is coming at this point, at the point of curtailment. So now this shear force, it is greater than two-third of what I can resist, what my beam can resist. So obviously, if it is greater, I will have to provide extra stirrups. So that extra stirrups, I am providing it in the form of two-legged 8-5, and the spacing of which I will have to take care based upon the minimum area and based upon the minimum spacing. So the spacing, it should be lesser of these two values, and beta, it is the area of curtailed bar, 25 bar, and this is the total area. So beta, I'm getting it as 0.44. After substituting, I'm getting the spacing of the extra bars stirrups, it should be 113 and it should be provided in an span of 0.75 d towards the mid span. So if I'm keeping this as the spacing, if I multiply this by 3, I will get what? 339, and 0.75 into d, it will be also coming up into this value only. So I will have to provide, I can like accommodate three number of stirrups. So I'm providing these three extra stirrups to take care of the shear curtailment, shear forces because of the curtailment of the tensile bars. Okay, so this was all about the curtailment portion I wanted to cover in these sessions. If you have any doubt, you can ask me.
Sir, what about the slabs? In the slabs as well, we have to follow AST by 3 and AST by 4.
Yeah, in slabs also we have to follow these provisions. In actually in
Uh,
slabs we have some other provisions. Point one L, the one which are, I don't remember it right now, but in the similar fashion which we follow in the beams, we have provisions for slabs also. I will take for that
actually,
slabs. Yeah. Okay.
for one-way slab, I had studied that this provision is applicable, but for the two-ways slab where there is that conditions, 50% should be at the top and
Yeah, yeah.
50%
You are talking
that,
about that. What?
yeah.
What?
That 1 minute.
What are you
What the
saying?
exact term? Restrained. 1 minute.
Hmm. Cranking.
Yeah, restrained slabs for the restrained slabs. Those provisions.
Yeah, but what do we call that? 50% it should be above and 50% it should be below.
That cranking part.
Yeah, that cranking it is being provided. Yeah. So,
So
yeah.
yes, sir. What should be the condition? What should we do?
Yeah, 50% we like bend it so that it will take care of the negative reinforcement at the support. And 50% we let it in the continue to the support only.
Sir, in the one of the detailings, I have seen three or four kinds of. I think detailings, in one of the detailings they were saying that AST by 3 and AST by 4, that thing
Okay.
should be followed.
Yeah.
Uh,
So in the next class, I will be solving problem on two-way slab, and I have planned to like also discuss on the curtailment part of the slab. So don't worry about it. Let me also like collect all those data and summarize all of them for you and explain you better. Okay.
Sir, please provide for the system of slabs as well.
For the system of slabs, what do you mean?
Means we have 2 to 3 slab panels.
Okay,
Are you,
continuous slab.
yeah, yes, sir. For the continuous slab,
Yeah, I will do
it
it. Don't worry.
beam on column, it is supported on that.
Okay, okay,
In that case, yes, sir. That
okay.
part.
I will do. Was today's lecture helpful for you?
Yes, sir.
Okay, so
This shear part was, I had studied it up, but the shear part was not clear to me. I had studied it in very long time ago, so it helped me to recall those things. But the shear part was not clear to me. This part got cleared right now.
okay, okay, very good. And are you are a BTech student?
No, sir. I was preparing for the competitive exams. I have completed my BTech last year.
Okay, okay. Have you done masters?
No, sir. No, sir.
Okay, that's fine. That's good. So we will be discussing on the curtailment of bars for slabs in the next class. Don't worry.
Okay, sir.
Was that all you have to ask?
Yes, sir.
Okay, then I would like to conclude this class here, and let's meet on next Tuesday, 6 to 7. Thank you.
Thank you, sir.